So now we want to actually calculate the value of the change in entropy for a chemical reaction. If we want to predict spontaneity, we need the change in entropy of the universe, which is going to be composed of the reaction and the change in entropy of the surroundings. So we're going to take these one at a time. We're going to start by looking at the change in entropy of the reaction. So how we actually do this is using reference data, thermodynamics reference data. So it's going to be very similar to our approach for calculating the enthalpy of a reaction, where we basically take the sum of the enthalpy of formation of the products and subtract it of the sum of the enthalpy of formation across my reactants. I do the same idea. So basically I look up the reference data for my entropy for the products. I look it up for the reactants and I'm good to go. You will note there is a slight difference between these, and that is that for our reference data for enthalpy, there are deltas because that's a change, whereas for the entropy values, these are absolute values. There's no delta in front of it. That is the entropy of that of that compound. And so this actually reflects a little quirk of entropy that for most thermodynamic properties, energy, enthalpy, we can't calculate an absolute value. But when I say that, I mean like an actual number of what is the enthalpy. That's why you never see H. It's always delta H, right? And so when we want to talk about the sort of inherent enthalpy inside of a compound, we use delta H, the formation enthalpy. What is the enthalpy of the reaction of going from elements to this compound? And so there's always a change. Enthalpy is always tied to a chemical reaction, to a change, to heating something up, to cooling something down. Never just, this is the enthalpy of this object. It's got 4 enthalpy or something like that. You can calculate entropy. You can say it's got 10 entropy or whatever it is. And that's unique. And the reason for that is because of the third law of thermodynamics. And the third law of thermodynamics is, it's ranked third. It's the least important. But the third law of thermodynamics tells us that for a perfect crystal at 0 Kelvin, S is equal to 0. So there's a couple things we're going to parse out. One, what is a perfect crystal? So a perfect crystal is this image of a solid that we've been looking at, or that we kind of use as our standard what a solid is. A perfect crystal is a solid where all of the molecules or atoms are arranged in perfect kind of patterns, that they are perfectly arranged together. In real life, things don't go so perfectly. There might be like a molecule missing or two, or a molecule gets unorganized. In a perfect crystal, everything is arranged perfectly. So that means you have a perfect pattern, right? There's a perfect arrangement, and most importantly, in a perfect crystal, there is only one arrangement. So that means it's very predictable what the relative positions of those atoms are. And then at 0 Kelvin, there is no motion. There is no molecular motion at 0 Kelvin. We know that Kelvin is an absolute temperature scale, so you can't go negative. And we know that Kelvin temperatures correspond to basically motion. So at 0 Kelvin, there is no motion. There is no motion of that object. It's all those molecules aren't moving. So basically, if you have a perfect crystal at 0 Kelvin, it's only got one arrangement. So if you know there's a molecule right here, you know where every single other molecule is because they follow the one arrangement. And so if you know where one is, you know where they all are because basically they follow that perfect pattern and none of them are moving. There's no sort of kind of wiggle room as to where they could potentially be. So there's one possible arrangement. It has 0 entropy. It is perfectly defined, no disorder, a beautiful, beautiful order. There's kind of some other parts of applications of third law of thermodynamics. One of the most important things is that you can't reach 0 Kelvin. So this is only in theory. You can never reach 0 Kelvin. Also, as the name implies, a perfect crystal ain't happening anytime soon. So these things don't, this is important that nothing actually has 0 entropy, but you can understand the entropy of everything else basically by how is it different from a perfect crystal. So we have this kind of theoretical idea of this is a perfect crystal. So if you have some solid that's not a perfect crystal at, 25 degrees Celsius or room temperature, you can understand and make, quantitative predictions as to, well, what is the entropy and how is it different from a perfect crystal? How is it different from being at 0 Kelvin? All right, so nice little aside with the third law of thermodynamics, but the actual reference information that we use can be found in tables. So this is a table that I have pulled off of sapling. This is kind of part of the sapling table. You'll note it starts, this is silver. It's alphabetical by symbol, by the first symbol. So metals are usually first, and you can see it just kind of goes down. You get silver, aluminum pops up, barium, gold, all sorts of stuff like that. So you'll note it's based on chemical symbols. So you're looking for the symbol, and it's going to be based off the first. You'll note that like silver chloride is up here. It's not in the chlorine section. If chlorine is first, eventually that would show up down there in the CLs. And so we've seen basically this table has delta HF. It has S, and then there's also these delta Gs. We'll get to those later in this chapter, and so we'll use those. And so you'll note also there's this little degree symbol that's on the top of them. That means not, so N-A-U-G-H-T, not. What that implies is that these values are at a pressure of 1 bar. Conditions really do affect your chemistry and that's part of it. What is the pressure? That's how you're different from being in a perfect crystal. But all of these were taken at 1 bar. So all of these calculations were taken at 1 bar. So you can generally assume 1 bar is generally the atmospheric pressure in most places, especially it's very close to what we have here in Baytown. And so that's a good kind of approximation that that we're always at 1 bar, or any sort of calculation you're ever doing, any chemical reaction you're ever going to do is at 1 bar. You will note that the temperature is specified. So if you were doing chemistry at a different temperature, you would need to get a different table. 298 K, that's 25 degrees Celsius. So we're going to kind of assume that everything's happening at that room temperature. Even our lab at Lee is usually at about like 20 or 21 Celsius. It's usually very cold in there. But still, the answers you're going to get from an analysis like this are still going to be pretty good, even if you assume it's 25 degrees Celsius. All right, so let's look at an actual example. What is the change in entropy for the following reaction at 298 K? It's propane gas plus 5 oxygens, gives me 3 CO2s and 4 H2Os, and I've already collected the thermodynamic data for these molecules. So let's see how it goes.
All right, so I want to know what is the change in entropy for a reaction. So we're going to be looking at some different types of entropy. Whenever we're changes, different changes in perspective, I was going to be thinking about, I want change in entropy, so I know that's going to look like delta S, and the change in entropy for what? And so it's going to be this chemical reaction. And so whenever we want an entropy for a chemical reaction, similar to how we've seen previously for enthalpy, what we can say is we know that delta S, we can say for like our reaction, is going to be the sum over the products of those S's minus the sum over reactants of the S's, where I'm going to use this reference data right here. So this table, I went through and found a reference table and chopped out only the relevant compounds, but you could look up a big table and find all of the relevant compounds. So when we're plugging these in, products, that's 3 CO2. So what I'm going to do is I'm going to take a 3 and multiply it by the S value for CO2. So I do incorporate that coefficient. Basically, this number implies, you can see it's joules per mole Kelvin. So this would be per 1 mole. Well, I have 3 moles in this reaction that I'm forming. So I'm going to do 213.8 joules per mole Kelvin plus 4 times H2O. That'd be 188.8 joules per mole Kelvin. And then from that, we're going to subtract the reactant side. So I just got the C3H8, find that, find the S, 270.8. Technically, this is multiplied by 1. Just like there's technically a 1 implied in front of there, but again, we don't have to write it here. Don't have to write it in math. That's why we have that form convention for chemical equations. 5 times O2 is 205.2 joules per mole Kelvin. We want to find all of that reference information. Just kind of arrange it, use all the reference information, plug on, and then it's just a matter of doing the arithmetic of all of those parts that we put them all together, and we get that delta S is equal to 100.3 joules per mole Kelvin. And so if we are given a chemical equation, this is kind of our generic equation for how to calculate delta S of the overall reaction. We need to look up the specific values for the different reactants and products and plug all of them in and combine to get our information for the overall reaction that we have right there.
Whenever we get a value for an entropy of a reaction, or really an entropy at all, we always want to think, does the sign make sense? So 100.3 joules per mole Kelvin, you can't really intuit if the value is appropriate, but we can think about the sign. This is a positive value, right? There's no negative in front of there. So that would imply that reactants to products is an increase in entropy, an increase in disorder. And we can understand why by trying to do those predictions that we've talked about previously. I have 1 plus 5 gas reactants. That's 6 gas reactants becoming 3 plus 4 gas reactants is 7. So I go from 6 to 7 gases. So 6 to 7 gases, that's an increase in the amount of gas. So that'd be more disorder. That's consistent with the idea of having more disorder, so more gas on the products means I would expect a positive entropy change. So this all checks out. So this makes sense. So I can at least check. If I had gotten a negative number here, I would know that it was wrong. I can't look at 100.3 and know, is that right? But I can figure out if something's wrong. Participation 1028, question 3. What is delta S for the following reaction? 3O2 gas becomes 2O3 gas, and there's some reference information to help you answer the question. This is the third question on participation 1028, due Tuesday, October 28th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. The reaction, what is delta S for the following reaction? The reaction is 3 oxygens becoming 2 ozones, and you have this useful information down here in the table that will be necessary to answer this question. Okay, another question for 1028. What's that, 3 now? Got a couple more videos left. Might find some more questions. Who knows? Let's watch the videos and find out.